incoherence. Take it away.
Great, thank you. So I guess this is the last lecture. So one thing I wanted to say was that I think we should all thank the organizers, because it's been a great 2 weeks and I really enjoyed it and they've done a great job. So thank you all very much. Okay, yeah, so right, so my third lecture is going to be about coherent groups. Okay, so in the first lecture, I gave you an example of an incoherent group. Yesterday, I gave you another tool to prove that things are incoherent, and maybe, you know, those two tools really allow you to prove a lot of the results that we have in some sense. And so today, I want to tell you about how you prove that things are coherent. Okay, so this is actually much harder, and there was a comment yesterday about that perhaps this is a low-dimensional phenomenon. And maybe I'll say some words about that at the end when I get to open problems. So, okay, how are you going to prove that something's coherent? Well, sort of the easiest example, but the hardest way to prove something is maybe you really understand every subgroup. Okay, so here's my example 0, abelian groups, right? If you have an abelian group, then you really understand the finitely generated subgroups, right? So if A is abelian and H is a subgroup of A finitely generated, then H is a finitely generated abelian group. Hence, H is isomorphic to a direct product of cyclic groups. Right, so, and there are finitely many cyclic groups in this product because it's finitely generated. And so you know how to present a direct product of groups, and you know that this is finitely presented, right? So if you really understand the subgroups, you can, you can get a handle on what's happening, right? And the same proof, so this same proof works for free groups, for instance. So, so similarly, right, subgroups of free groups are free. So if H is a subgroup of a free group which is finitely generated, then it's a free group on some finite set for I finite. Hence, H has a presentation of this form. Okay, and so it's finitely presented. It has a presentation with no relations. As an alternative proof using compact cores, and this also, so I should say that this also works for surfaces. Also works for surfaces. Right, so I'm just going to say it in words. If you have a, right, if you have the fundamental group of a non-closed surface, then it's free, so you can just appeal to the previous thing. If you have a closed surface, then every subgroup is either the fundamental group of a closed surface, which has a presentation with one relator, or it's a free group. So you're done in either case. Okay, so perhaps you could really understand the subgroups, and this sort of idea. If you think about how to write down presentations of polycyclic groups, this idea for polycyclic groups, noting that polycyclic groups, all their subgroups are polycyclic, and polycyclic groups are finitely presented. Okay, so this is an exercise. And I was trying to think if you could apply this to more classes, but these were the only classes where I had any, these were the only classes where I had any ability to really say this is exactly what the subgroups are, and I know enough about these subgroups to say that they're finitely presented. Okay, so where do you go from here? Well, in some sense, we've done we've done free groups, so that's like one-dimensional spaces. We've done surfaces, so that's 2 manifolds. And so the next place where people maybe went was 3 manifolds. Okay, so let me tell you the story of 3 manifolds. So it turns out that 3 manifold groups are coherent, which is this corollary. So let me, and the reason they're coherent is what's known as a compact core argument. So this is, this is sort of a good way to prove that something's coherent, is to prove that it's the fundamental group of a compact space. And so what Scott proved is he said that if you have a 3-manifold, M be a 3-manifold, pi1 of M finitely generated, then there exists a compact submanifold N such that the inclusion, right, the inclusion induces a map from pi1 of M, from pi1 of N to pi1 of M, and he proved that this map is an isomorphism. Okay, and so corollary, right, fundamental groups of compact spaces are finitely presented. So the corollary is that pi1 of M is finitely presented, right? And so if you want to apply this to see that 3-manifolds are or 3-manifold groups are coherent, you take your 3-manifold, you take your finitely generated subgroup, you take the cover corresponding to your subgroup, that's also a 3-manifold, and its fundamental group is finitely generated, and so now you can find a compact core. And I sort of want to give you a sketch of Scott's theorem, because I think it has sort of, there's one really key great idea, and you can sort of see why there's sort of a reason why this idea is very 3-manifold topology. Okay, so how do you prove something like this? So here's a sketch. So sans some details. So the first thing you do, which is not very hard, I mean, this is what you can sort of do this in any case where you have a finitely generated group, is that there exists a finite graph K and a continuous map F from K to M such that F star from pi1 of K to pi1 of M is a surjection. Right? You can do this whenever you have a whenever the fundamental group of a space is finitely generated, you just represent those generators by loops, take the union of those finitely many loops, that gives you a graph, and then you just map that graph in, and that gives you something that's surjective. You can assume in the 3-manifold case, and let's just assume this, you can assume that this is an embedding. Okay, so this is a small corollary. If you ever sort of put in a 3-manifold and you had a point where it was not an embedding, you can just move those things off each other. I mean, the proof is really this. Right? That really is truly the proof. And so because it's an embedding, what you can do, I think this is true even if it's not an embedding. So we can just sort of thicken this graph up to a 3-manifold. So let M1 be the delta neighborhood of F of K for some delta bigger than 0. Okay, so take a little neighborhood of this graph that you've embedded in your 3-manifold. Okay, and so M1 is a submanifold, and the map from K to M factors through M1. So the inclusion from M1 to M is also a surjection on fundamental groups. Is a surjection. Right. So now I've got now I've gone from a graph with a surjection to a submanifold with a surjection. Right. That's sort of the first part. And so then, okay, if phi is an injection, then you're done. So then just take n equals m1. Okay. So if you've done this and it turns out that your fundamental group was free and you now have your submanifold, you can just stop. But if it turns out that it's not an injection, right, you have to do something. And what do you have to do? So so the thing that happens is that if phi is not an injection, then, so what does that mean? Well, that means that there is a non-trivial element of the kernel. And so what that really means is there exists gamma, a loop in M1, such that gamma bounds a disk in M. Right? You have this loop. I mean, I haven't even said the words that it's non-trivial, but so the homotopy class of gamma defines an element of pi 1, and this is a non-trivial element of pi 1. And it bounds a disk in M, right? Because it's trivial under the inclusion map. And so now, so call this disk D, this disk D, and look at D intersect the boundary of M1. Okay, so M1 is probably a submanifold with boundary unless you got very, very lucky. Okay, so now you have this disk, right? Well, this disk lives inside M, but this loop is non-trivial in M1. So in particular, this intersection is non-empty. Okay, and so now by sort of a general position argument, you're intersecting two two-dimensional submanifolds. So you're intersecting two-dimensional. Sorry, let me try and say this without telling you a lie. You can assume this disk is immersed, and now you're intersecting two immersed submanifolds in a three manifold. And so generically, those are going to intersect in an immersed one manifold. And so the upshot is, this is a point where you're really using three-dimensional topology. What you can get out is a curve on the boundary of M1 that you can get out a curve alpha on the boundary of M1 such that alpha is not equal to the identity in the fundamental group of M1, but alpha is equal to the identity in the fundamental group of M. Okay, so you've taken this loop inside your three manifold, and using three-dimensional topology, you've got yourself a loop on the boundary. Okay, and so now you have this loop on the boundary. Now this loop on the boundary bounds a disk. So alpha, so by sort of taking a minimal such loop in some sense, we can assume alpha actually doesn't just bound a disk in M, we can assume that it bounds a disk in M with M1. Right? Because if every disk had to go back into M1, then sort of there's a smaller loop when that disk leaves M1 again, and you just take this smaller loop. So you sort of, some sort of nesting thing going on here. Okay, so what have we done, right? Started with a graph, we got a three manifold, we found a loop which was non-trivial but was in the kernel, and this has given us a loop on the boundary. And now we're going to use another part of three manifold topology. So, three-dimensional topology, which I'm not going to state precisely, but it's the loop theorem of Papakiriakopoulos. Loop theorem tells us that implies. So the loop theorem says that if you have a loop in the boundary of a three manifold that bounds a disk, then you can actually make it bound an embedded disk. Okay, so this implies there exists embedded D2 in M without M1 with boundary of D2 equals alpha. Okay, but so now you've got this embedded disk. So now what you can do is you can take M1, you can take this embedded disk, you can take a little neighborhood of this embedded disk. So let M2 be M1 union the epsilon neighborhood of this D2. Okay, and this is now a 3-manifold. So this is a submanifold of M. We still have the fact that pi1 of M2 surjects pi1 of M. Okay, but now right, we still have this surjection, and so now if it's an isomorphism, if injective n equals M2, if not, repeat. And so now you can repeat this process with M2, right? So if this map is not injective, then there's a loop in M2 which bounds a disk. So now you can use these 3-dimensional facts to give you a loop on the boundary which bounds an embedded disk. And you can take the union of a neighborhood of that embedded disk and get M3, and you keep doing this. So the question you should be asking is, why does this process terminate? Okay, so you can do this in any setting, right? If you have a finitely generated subgroup of some group, you can take a finite graph and then you can say, oh, well, here's a loop which is not trivial. Let me just put a disk onto that. And now I get some new embedding. Here's a loop which is in the kernel, add some disk onto that. And you can keep doing this. And the fact that there are incoherent groups tells you that this doesn't always terminate. So why does it terminate in this case? And the reason it terminates, so why does this terminate? And so the reason it terminates is that if you look at the sum, so what have I, so the sum of the genus of the let's say it like this, the sum of the genus of the boundary components of Mi decreases. Okay, so it's an exercise that I've given you on my list of exercises is when you add this disk, what have you done to the boundary component where this disk was added? Well, if you think about it, what you've done is you've cut open along this curve and then you've capped off this thing, and you're going to have reduced the genus. And if and the thing is that if it's 0, then we're done, right? So if the boundary components are all copies of S2, then they have no non-trivial curves on them. And so in particular, this process has to stop there. So you're reducing some complexity bound, right? And so just to sort of sum up, so as I say, there were 2 key points of 3-dimensional topology. One was getting this loop on the boundary, was using the loop theorem to fill this loop with an embedded disk. But to sum up, the sort of key ideas that I want you to take away from this proof are you start with some finite graph and a surjection, right? This is something you can always do. And then you just start adding these disks, right? And this is like adding relations one at a time. And sort of the key thing, the key thing that you have to try and do is find a way in which this terminates in a finite amount of time. Like, why do you know you have to stop? And when do you, and sort of, there's another algorithmic question here, like is there an algorithm which tells you when you have to stop? So for instance, in a 3-manifold, there is sort of an algorithm. You know that once the boundary components become pi1 injective, then you can stop. And so for 3-manifolds, knowing that this terminated in finite time was really a combination of this loop theorem and a combination of the Euler characteristic or the genus of the boundary. Okay, but this sort of idea works more generally in other places. And so another very recent development is the idea of negative immersions. right? So this is, so yeah, so we can allow this to prove, so we can sort of leverage this to prove a coherence result in the case of negative immersions. So we say that a 2 complex X has, oh, that's not what I want to do. We say that a 2 complex X has negative immersions if whenever we have a locally injective map of 2 complexes, so here, this is a 2 complex, then either, right, either Y is a point, so this is something you can't avoid. Y has a free face, and so this terminology comes from simple homotopy theory. And so what that means is that Y sort of looks like, Y is some sort of blob, and in this blob you see a triangle which has an edge such that there are no other triangles on the side of that edge. And the point about having a free face is that if you have a free face, you can just push in on that free face and you can homotope this triangle away in sort of the most naive, you know, when I first started thinking about homotopy theory, I thought that this was pretty much what you did. You just sort of started like doing these things. But if you look at Bing's house with 2 rooms, that doesn't have any free faces, but still is contractible. So, okay, so this is like, you can apply some sort of very easy homotopy move, or the Euler characteristic of Y is less than or equal to some C, so, or some C times the number of 2 cells in Y. Cells in Y. Okay, so you're in the, so you sort of have these 3 cases, right? Either you're a point, or you can make some easy adjustment, or it turns out that you have negative Euler characteristic. And the point is that this, I mean, these 2 things are sort of unavoidable, right? So you're always going to have a locally injective map from a point, and you're, you know, if you have a maximal tree, you could think about, you know, if you have more than 1 vertex, then a tree is going to be something that has a free face. And these things are going to have positive Euler characteristic, right? But then in this 3rd case, you're saying that you have negative Euler characteristic, and that's really what this negative is, right? So it's essentially saying that if you immerse, then either you have negative Euler characteristic, or you can make some sort of edit which makes you simpler, or you're a point. And so the point, so the reason why you might care about this from a perspective of coherence is this 3rd condition. This 3rd condition pretty much allows you to prove coherence. So it's a theorem of Danny Wise that if X satisfies negative immersions, then pi 1 of X is coherent. Okay, and the proof is contained in the survey, which is on the website. But some sort of idea of the proof is that it's similar to 3 manifolds in a sense. So similar to 3 manifolds. 3 manifolds, right? In the sense that the condition, you do the same thing, you start adding relations. The condition on the Euler characteristic of Y tells us when to stop. Tells us we can stop adding relations, right? So stop adding relations after some point, right? So the point is that if you fix the 1 skeleton and then you just start adding 2 cells, every 2 cell you add takes the Euler characteristic up by 1, right? Because the Euler characteristic, right, just as a reminder, you know, the Euler characteristic is the number of vertices minus the number of edges plus the number of faces. So when you start adding faces, you're increasing the Euler characteristic. So if you know that the Euler characteristic can't get too large, then you know that you can only add so many faces, and so you know when to say, well, actually, this process has to terminate because otherwise my Euler characteristic is sort of going to go off to positive infinity. Right, so this is another, right, so it's sort of a slightly similar idea, and you're using this condition on Euler characteristic to tell you when to terminate. instead of something about the boundary. Although in some sense, the boundary, it was really the Euler characteristic of the boundary. It's all Euler characteristic. Okay, so I want to give you a sketch of one more theorem, and it's a theorem that I think is very, very useful. And it's a theorem that I think that the proof in the sort of the original proof is maybe a little bit hard to read, and so I wanted to give you a sort of presentation of a sketch that that makes the proof sort of more modern. Okay, so this is a theorem of Carousel and Solitar, and it's sort of a compact core style theorem, and we'll see why in a second. So if we have, let G be, so let G be the fundamental group of a graph of groups, a graph of groups with coherent vertex groups, and slender edge groups. So I'll define slender in 2 seconds. Then G is coherent. And so just to say, slender is also sometimes called noetherian, which is maybe actually, I think noetherian might be a better thing to call it if you've studied rings a little bit. So it's that all subgroups are finitely generated. Okay, so examples, finitely generated abelian groups, polycyclic groups, and those are sort of the only examples. These are the only examples that I know. So actually, Tarski monster groups, right? So Tarski monster groups are 2 generator groups where every subgroup is cyclic of some order. Okay, and so in particular, finitely generated. And it's actually a question in Danny Wise's survey whether a finitely presented slender group is virtually polycyclic. So maybe for finitely, so all Tarski monsters that we know of are infinitely presented. So maybe once you include the words finitely presented, and it should be said here that in this case they all will be finitely presented, because in particular they're finitely generated subgroups of coherent groups. So perhaps you can only get polycyclic. Okay, so I want to sort of give you a sketch, and the thing is that the proof really isn't that hard. So let H be a finitely generated subgroup of G. So then the thing is that G acts on the Basset tree for this graph of groups. Okay, and so you get an action of H on this Basset tree, and so this gives you a way to write H as a graph of groups. And in fact, it's a relatively easy exercise to see that there exists T prime subset of T H invariant such that T prime mod H is compact. Okay, so this uses so a key thing here is that this uses finite generation. Okay, so because you have a finitely generated group, you can get a co-compact subtree. Okay, and I'm very happy to talk about that, but let me just leave it as an exercise for now. And so now you have this co-compact subtree. You've now got a finite graph of groups decomposition for H, right? Because a graph of groups decomposition is equivalent to an action on a tree, and because your quotient is compact, you have a finite graph of groups decomposition. Okay, so let let VE be the graph for T prime modulo H. Okay, so these are the vertices and edges. GV vertex group associated to V, GE the edge group associated to E, right? So you now have this finite graph of groups with these vertex groups and these edge groups. And the thing is that H, so there's sort of just, this is really the key point. So Riley told you how to write down a presentation for a graph of groups, which I've already used in these lectures. But the point was that this presentation had as generators the union of the vertex groups. So H is generated by the union of the vertex groups. But since H is finitely generated, there exists SV, a subset of HV, finite, such that, oh, sorry, this should be GV. Maybe I should have called these things HV. There exist finite subsets of each of the vertex groups such that H really, right, instead of thinking about it being generated by the whole vertex group, you can think about it being generated by these subsets, right? So if you have a, right, so the point here is that if you have a finitely generated and an infinite generating set, then you can take some finite subset which generates, okay? And so replace, so what did I say? So H is generated by the union of these things, so replace GV by the group generated by SV and the disjoint union of the G's where the terminal vertex of E is V. Okay, so you replace a vertex group with the subgroup generated by this finite subset you needed for H and the union of all of the incoming edge groups. Okay, and this is and so then one sort of, right, you now have a graph of groups where you haven't changed the edge groups and you may have changed vertex groups, but the point is that H is a subset of the let's call this, I guess let's call this HV. So H is now a subset of the disjoint union of HV, right? So you've sort of thrown away your original vertex groups and you've taken these smaller ones. It turns out that they aren't really smaller, but they sort of seem it. Okay, so, and in fact, right? And in fact, everything you've chosen was contained in H. So in fact, H is equal to the subgroup generated by the disjoint union of the HV. Okay, well, the thing is that each of these edge groups is finitely generated because we're slender. So finitely generated by slenderness. Is that a word? So each of these edge groups is a finitely generated group. So in particular, HV is finitely generated. So each is finitely generated. Right? But HV is a subgroup of a vertex group for my original splitting for G, right? Because H is acting, and in the action of H, all of the vertex stabilizers are subgroups of the vertex stabilizers for G, because the action was just factoring through the action of G. So HV is finitely presented. Finitely presented, since vertex groups were.
You mean H?
No, sorry, I mean the I mean HV. I think
Okay.
you've seen the end of the proof.
Sorry.
You know the conclusion that's about it. So the thing is that, so each of these new vertex groups is a finitely generated subgroup of a coherent group. So it's finitely presented. And is that now what you've done is, so now we've written H as a graph of groups with finitely presented vertex groups, right? These HVs and finitely generated edge groups. And if you have a finite graph of groups, right, you can write down a presentation for your graph of groups. Riley did this, and I think the one that Riley wrote down is possibly infinite. No, okay. So and the point being that you just have to do things with generators. You just have to do things with generators of edge groups, right? So as long as all the edge groups are finitely generated, they're only adding in finitely many relations. All your vertex groups are only adding in finitely many relations. So this implies that H is finitely presented. Brackets, graph of finitely presented groups. Finite. Graph of finitely presented groups is finitely presented. Okay. So it's actually pretty easy. Modulo one very small exercise is very easy. Okay, so you just use the action on this tree. It's so easy that I'm once again ahead of myself. Well, that's fine. That's fine. That gives me time to talk about open questions. So so the thing is that this, for instance, allows you to sort of reduce things in certain ways. So in Riley's lecture, she briefly mentioned the JSJ splitting, which is about splitting groups along cyclic edge groups. And so if you want to prove that something's coherent, what you can first do is split along cyclic subgroups, and then look at each of the pieces. So let me add in a page before I go to my open questions. So application. So for instance, for hyperbolic groups of one-ended hyperbolic groups, you have this JSJ splitting, which really lets you write your hyperbolic group as a graph of groups. Vertex groups are either surface groups, virtually cyclic, or what's known as where rigid sort of means that there aren't any outer order morphisms, and edge groups are virtually cyclic. Right? And so the point of this theorem of Carousel and Solitar is that now, if you want to study coherence for one-ended if you want to study coherence for infinitely ended hyperbolic groups, then your first call is to use Dunwoody's accessibility theorem to tell you that you can split it as you can split along finite subgroups. So and then you can use the JSJ decomposition to say, well, actually, I only really care about these rigid pieces. So Carousel and Solitar reduces coherence for, let's say, one-ended hyperbolic group G to coherence for rigid pieces. Right? So this sort of allows you to do, so the point about the Carousel-Solitar theorem is it sort of allows you to do reductions. You can split your group up and then you can glue it back. You can, you prove that the pieces are coherent and then you glue them back together and you know that the result is coherent. And there's an exercise So another exercise that I think is a great thing to do is a theorem of Drom's, who answered the question of when is a right-angled Artin group coherent? And it turns out that there's a rather simple graph theoretic condition which tells you exactly when a right-angled Artin group is coherent. And the point and the real sort of heart of that theorem is that if you satisfy this graph theoretic condition, then you can split over an abelian group. And so you can sort of induct, you can get things of lower complexity. And you know, I recently used this theorem to prove something about of one-ended hyperbolic groups in the same way. You sort of cut into pieces and then you understand each piece is coherent and you're gluing them together along things that are nice in some sense. One thing that should be said, one thing that I would like to say is that this theorem is hard to generalize in some sense. So one issue. So I think the idea is is a very nice idea, and it's once again it's sort of a compact core idea. Okay, you have this group acting on a tree. The point is you can find a co-compact subtree, and that's really telling you that it's finitely presented. One issue is you can't. It's hard to replace slender. Can't replace slender. So for instance, it's so you know I haven't found anything that you can really replace slender with, and this theorem still holds. But there probably is. I probably just haven't thought hard enough. False if edge groups are free. Groups are free, for instance. Right. Right. So you can, I mean, it's very easy. Once you're allowed free edge groups, you can just amalgamate two copies of 2 times Z along a copy of F2, right? And this gives you something, this is F2 times F2, right? So you started with 2 coherent groups, namely F2 times F2, namely F2 times Z, right? Those are coherent. If you amalgamate them along a free subgroup, you get completely stuck. Okay, does anyone have any questions before I move on to talking about open problems and problems that, you know, a list of open problems that I would love people to solve? Okay, so, right. So, okay, so I think at the end, yes. So sort of giving you some idea of some techniques, right? You can do things like, right? You can embed F2 times F2. This is quite a good way to show that something's incoherent. Virtual fibering is another great way. And if you want to prove that something's coherent, then I think the first thing to do is use the Carousel and Solitar theorem to reduce complexity in some sense. So what are some open questions? Where are some places where we still are completely stuck? Okay, so some of these I've mentioned already. So the first one that I want to mention is SL3Z. Okay, so this is an amazingly large open problem, whether SL3Z is coherent or not. And I don't know, I don't understand 3x3 matrices, so so I have no real input on this. But one reason why it's hard is so it doesn't virtually fiber. Doesn't virtually fiber. Doesn't contain F2 times F2. Okay, so it not containing F2 times F2, I'm actually struggling. I didn't find out the reason why that's true. The reason why it doesn't virtually fiber is because it has property T. And actually, this is a similar thing for SL2 of Z adjoin 1 over P. So Z adjoin 1 over P, I don't know, it maybe amazes me that this group is finitely generated, but it's actually quite a nice group. You can actually write this as an amalgamated free product of 2 free groups along a finite index free subgroup, if you pick this correctly. But once again, it doesn't virtually fiber because it turns out that it satisfies some form of super rigidity. Namely, it satisfies that any normal subgroup is either finite or finite index. So it's very hard to find normal subgroups that, well, no normal subgroup is going to do it because finite groups are finitely presented and finite index subgroups are finitely presented. And also you can't get virtual fibering because I want to say you can intersect things and take normal cores. I'm a little bit nervous, but I'm pretty sure you can't get virtual fibering in this case. And as far as we know, it doesn't contain F2 times F2, although I don't immediately see a proof of that. So these are sort of two matrix groups, right? They're pretty easy to write down. You can, matrix groups are maybe they're maybe some of the first groups you meet. So yeah, I think those are two great examples. Random groups. As I said earlier that we managed to prove that two generator random groups. Oh, sorry, just as an aside, I'd love to know why it's finitely presented. I don't really fully understand. Other than somebody once convinced me that this equality is true. Sorry, SL2Z1 over P. Because Z1 over P seems like quite a large ring. So anyway, let me not get sidetracked by my own lack of knowledge. So random groups. So we recently proved that if you have a two generator random group, then coherence is just a question about Euler characteristic, which is really just a question about number of relations. So if it has two or more relations, it's incoherent. If it has one relation, it's virtually free by cyclic. And if it has zero relations, then it's a free group. Can you extend this to other random groups? Okay, and so so for the negative Euler characteristic case, we proved that they are coherent. And for the Euler characteristic zero case, we proved that with non-zero probability, they're all virtually free by cyclic. And actually, I believe that it should be possible to upgrade that non-zero probability to probability 1. Okay, so really the interesting case is Euler characteristic bigger than 0. And there are some sort of ideas here where, the idea, so one idea that you could try and pursue is prove that they virtually fiber. So this is perfectly reasonable. Right, so, and to prove they virtually fiber, you could maybe do things like compute their L2 Betty number. That's what we did in a paper, whatever the L2 Betty number is. Groups acting on a product of two trees. This is a great question. Even just more examples, right? So groups acting geometrically on a tree are really very nice. Groups acting geometrically on a tree are virtually free. So they're coherent. But the second you take a product with a second tree, just all hell breaks loose. So the thing is, there exists simple groups. So there are these Berger-Moses simple groups that act on tree cross tree. Okay, and so they definitely don't virtually fiber. They have no normal subgroups, let alone maps to Z or finite index subgroups. But I think in the cases we know, there's a paper of RAAGs that shows that certain of them are incoherent and certain of them do contain an F2 times F2. So potentially you could show that they all contain F2 times F2, or you could try and do something there. But I think if we knew, even if you didn't put this question to bed, if you just could give some criterion that would tell us when these things are incoherent, I think that would be quite nice. And I don't feel like I can give an open problem session about coherent things that are worth thinking about without mentioning one related groups. So just groups with finitely many generators and one relator. These were first studied by, these have been studied for a very, very long time, and it even goes back in some sense to the work of Dane on surface groups. And there are some results. So there are results of Helfer and Wise and Lauder and Wilton showing that in certain cases these things are coherent. But basically we don't know. And okay, this one's very hard. And I don't really have any grand ideas on this one, I should say. Okay, so those are some like specific, are these groups coherent or not? now I want to ask some sort of more general questions. So firstly, when is a graph of free groups coherent, right? So if you have a graph of free groups with cyclic edge groups, then this theorem of Carousel and Solitar tells you it's coherent. So what about if you have a graph of non-abelian free groups with non-abelian edge groups? Is that coherent? And so this would include SL. This would include SL2 of Z adjoin 1 over P, based on the knowledge I have, or maybe just the case, or just, you know, it's probably worth just thinking about the case of you amalgamate you amalgamate just two subgroups along a free subgroup. And I think this case is even, so it turns out that if, let me try and not tell you a lie. So I think this case is even open if you just double. So if you just take 2 copies of Fn and you set an infinite index subgroup equal to itself in each one. I think we don't even know then. It turns out it's incoherent if it's finite index. This was a proof of Baumslag. But for infinite index, I don't think we know. And I think the answer, so my guess is that these things will be incoherent. The next thing is a coherent group with property T. So, so sort of Federico talked a very little bit about property T. He mentioned it in that it allows you to create expanders. It turns out that every property T group we know is incoherent. If you could prove coherence for SL3Z, SL3Z is a property T group, so that would be a, you know, you could kill 2 birds with 1 stone. But even just finding a coherent group with property T, I think would be really interesting. We've seen a lot of, so today, you know, I mentioned negative immersions, and yesterday I talked a lot about Euler character, and there seems to be a deep connection. And amazingly, we don't know of any non-trivial coherent group with positive Euler characteristic. Do I need to? I'm always nervous. People always flag me on this question and tell me that I need to add in an extra adjective. So let me be safe. Non-trivial infinite group with positive Euler characteristic. Right? We really just, like, somehow, I mentioned this after the talk yesterday, that constructing incoherent groups with negative Euler characteristic, you can sort of cheat by taking direct products with free groups. But to create coherent groups is actually very hard. And it should be pointed out that Carousel and Solitar won't really help you, because as far as we know, all of the edge groups would have to have Euler characteristic 0. And so the Euler characteristic is just the sum of the Euler characteristic of the vertices. So somehow, like, you really want something. You could have one that splits as a graph of groups, but that you can't somehow create one from coherent groups using Carousel and Solitar. That's one, or without doing something else. Is coherence a quasi-isometry invariant? So this is a great question that just seems really, really hard. And in fact, you know, if you could understand, if you could get a coherent group which acts on a tree cross a tree, then you'd be done.
I'm confused because I thought you said that was found. Did you say that there were groups?
Sorry,
like this?
Every group we know that acts on a tree cross a tree is incoherent.
I see. Okay.
Yeah. Sorry. That's the statement that is currently true. So, is it a quasi-isometry invariant? And somehow, you know, this seems maybe quite hard. I'd love to talk more about this, but maybe now's not entirely time. And finally, just to finish, a couple of questions about virtual fibering. So I mentioned random groups, and you know, I said that if you wanted to prove they were incoherent, you could prove they virtually fiber. You could prove they're incoherent without proving they virtually fiber. Okay, so SL4Z, for instance, is incoherent, but it doesn't virtually fiber. So these 2 properties aren't equivalent. And so I think it'd be really interesting if you knew they virtually fibered. Okay, and so in the same vein, you know, this question is maybe quite personal to me, is the question of, do hyperbolic free-by-free groups? So here, just to say, I mean Fn by Fm n comma n greater than or equal to 2. Do hyperbolic free-by-free groups virtually fiber? So in this recent paper with Stefano Verdusi and Genevieve Walsh, we actually can give examples of free-by-free groups that don't virtually fiber. So you definitely need this hyperbolicity assumption. But our groups are maybe very large in some sense, and it would be interesting to try and find a small one that doesn't virtually fiber, or prove what conditions you need on the automorphisms for it to virtually fiber. And there are sort of a ton of other open questions. So most of these questions you can, I think all of these questions, maybe except that very last one, are in Danny Wise's survey, right? He has a very long list of open questions. And I think there are a lot of really great questions there. And I've just cherry picked about 12 that I wanted to tell you about. All right, so I'm going to stop there. Thank you all very much.